Assalamualaikum. Let's continue. We are looking at linear variational problems coming from finite element discretization of PDE. Now we are look at Helmholtz problem and the solution of that. This is a connection of weak form and the strong form. Now we make connection between variational form equation and finite element approximation. Finite element has a solution that converges to the solution of variational problem itself. If the problem is smooth enough, then it's actually the strong form solution. Okay, let's go to general again. Topic 4, Galerkin approximation of linear variational problems. Let's consider more general. Assume that we have a well-posed linear variational problems on HK connected to a strong form PDE. Now we would like to approximate it. This is done in general using the Galerkin approximation. In this definition, we define what is Galerkin approximation. Consider a linear variational problem of the form: find U in HK such that BUV equal to FV for all V test function in HK. For a finite element space VH contained in a subset V, which is equal to HK space, the Galerkin approximation of this HK variational problem seeks to find UH in VH such that BUHV equal to FV for every V, the test function, for every test function in VH. Now VH is the finite element, UH is the finite element solution. Hence, these definitions explain a linear variational problems in the form of finite element. We just restrict the trial function U and the test function V to the finite element space. C0 finite element spaces are subspaces of H1. C1 finite element spaces are subspaces of H2 and so on. If BUV is continuous and coercive on HK, then it is also continuous and coercive on VH by the subspace property, because we state that VH contained in HK. Hence, we know that the Galerkin approximation exists, is unique and is stable. This means that it will be possible to solve the matrix vector equation. Moving on, if we can solve the equation, we would like to know if it is useful and what is the size of the error U minus UH, which is the difference between the exact solution and the finite element solution. For Galerkin approximation, this question is addressed by CS lemma. Okay, this is CS lemma. Let VH contain in a space V and let U solve a linear variational problem on V, whilst UH solve the equivalent Galerkin approximation on VH. Then the difference or the error U minus UH in V norm is bounded, is less than to a constant m over gamma minimum U minus V in V space. Here m and gamma are the continuity and coercivity constants of BUV respectively. Okay, next we will talk about interpolation error in HK spaces in the next video.